Hi everyone, welcome to this session on embedded microcontrollers. Today we are going to understand how tiny chips power the entire world around us, from your smartphone to cars to washing machines and to even the satellites and rockets. By the end of this session, you will not only understand what an MCU is, but also how it thinks, senses and controls the real world system. Here is what we will cover today. So what exactly is an embedded MCU? Its core components, the brain, that is the microcontroller core, memory systems, input or output interfaces, timing and control peripherals, data converters, communication interfaces, and finally a powerful summary. Let's understand this step by step. So let me ask you something. When you press a button on your washing machine or unlock your car remotely, so who is actually making the decisions behind the scenes? That's the microcontroller, and we call it as MCU in the shorter form. An MCU is a small computer on a single chip that takes input like a sensor data or like any other digital inputs like a switch, then it processes them and gives the output like turning on a motor or turning on an LED, anything, right? So in simpler word, what it does is it sense, think and act. That is what an MCU does. And also let's understand the MCU components. So an MCU is not just one block. It's a combination of multiple functional units working together. Think of it in a way. So CPU is there, which is the brain of the MCU. Then you have memory, which is for the storage. You have inputs and output ports for the communication doors. So like for interaction with the external world, it is required the input and output ports. Similarly, peripherals are the special workers, right? So certain special work, certain privileged level of works that is to be taken care by the peripherals. So all these things are integrated into the single chip. So the first part to understand is the MCU core, which is the brain of it, right? So heart of any MCU is the core. So it executes instructions and controls everything. So the popular cores that we have currently is ARM Cortex based cores. Okay, so Cortex M is normally utilized for the microcontroller based SoCs. Similarly, we can have now RISC-V SoCs or RISC-V based cores. 8051 which had Intel x86 based cores. Okay, so if you think of it in a way, the CPU cores which are there in microcontroller, it is just like the brain, and MCU you can consider as the whole human body. So the core decides what to do, when to do and how to do, and everything in the MCU starts from here. Now imagine a brain without the memory. Impossible, right? So MCU has also the memory, and this is of two different types. So one is the flash memory, which stores the program, that is the code section, and this is non-volatile in nature. So non-volatile means whenever there is a power on reset, the codes are not erased from this kind of memory, right? So this is flash memory. Then the second type of memory is the RAM memory, which is very fast in nature, but it stores the temporary data because it is volatile in nature, right? So that means whenever there is a power on reset, what will happen is the data is erased from this. Okay, so consider flash is something which is your long-term memory, and RAM is something, it's like something came into your mind, you just noted it down in a scratch pad or a notepad or in a piece of paper, okay, which doesn't have a long-term storage, right? So flash is for long-term storage and RAM is for the short-term storage or the temporary storage, but it is very, very fast in nature as compared to the flash. Now let's understand the inputs and outputs. These are used typically for interaction of MCU with the real world. So consider an example of inputs, right? If you have a button press, Okay, that's a pure digital input. That means when you have a button pressed, so either with the press of button it is connected to the supply voltage, that means it becomes 1, or it is connected to the ground, so it becomes 0. Okay, or the input can be an analog input, like there is a temperature. Suppose I have an LM35 sensor where what happens is temperature is converted into an analog voltage, so the input is then an analog input, right? Further, again, we'll understand in the further slides how this analog voltage is processed, right? Similarly, for output examples, if we see, we can have different categories of output. We can have directly just making a turn on or turn off of LED or a relay. Okay. Similarly, we can have a motor speed control or a motor control kind of thing, where you just turn on a motor, turn off a motor, or control the speed of a motor using those output pins. So basically, these are like pins. So you can have certain pins which is having input configuration, you can have certain pins which are having output configurations. Okay. So without input and output, the MCU is blind and mute. Timing is everything in the embedded system. Now this timing and control peripherals are there for this purpose. So they are used to create the delays. Okay, so basically if you are seeing a blinking of LED, so there is some delay of on period and there is some delay of off period. So who is used to create those accurate delays? That is the timers, right? Similarly, they are also utilized as the counters. So when they are used as counters, they are used to measure the time period and frequency of an incoming signal, right? Similarly, they are also used to generate pulse width modulation or PWM. So PWM is basically, if you understand, there is something called as a duty cycle. So in high power or if you say high frequency signals, what happens is the duty cycle is varied and accordingly the signal level also varies. So we can utilize this to control the intensity of the light, or suppose an LED, or we can utilize this to control the speed of a motor. Okay, so when you say duty cycle is very high, the speed becomes very high. When the duty cycle is very low, the speed becomes also comparatively low. Okay, so this timing and control peripherals are typically useful for rhythmic functioning of the embedded system. Okay, and that's why we call the clock and rhythmic functioning, both are controlled by this timing and control peripherals. The data converters. Now this is something interesting. Okay, so in real world, whatever data we see, they are ideally analog in nature. So be it a temperature data, be it a pressure data, be it accelerometer data, okay, or be it in the petrol pump, you see the volume of liquid that comes. They are all analog in nature, right? But as we understood, in MCU, the core processes only the digital data, right? So how do we connect both of them? So for that, we have data converters. So we have two different types of data converters. One is analog to digital converter, the other one is digital to analog converter. So as I told the temperature sensor example, right? So temperature sensor data is an analog data. So when that analog data comes, there is an ADC which converts this analog data into equivalent digital data so that the core can process this particular data, right? Similarly, suppose this embedded system wants an output, that is an analog output. Let's say you want a sound output. Okay, so when you want a sound output, that is analog in nature, but the data that is provided by the core is digital in nature, right? So how it is converted to a equivalent analog data? By using DAC, that is digital to analog converter, right? So these are the typical understanding of the data converters. Now MCUs don't work alone, they talk to the devices, and many protocols are used for this purpose. So a single MCU, consider in a car. Okay, so in a car there might be a separate microcontroller which is utilized for the headlight section. Okay, there can be a separate microcontroller which is utilized for the let's say steering. Okay, there might be separate microcontroller which is utilized for the gear, separate microcontroller for the other things like wiper. Okay, but what happens? All of them should work together. That means information from one should go to another. right? So when we have lots of different microcontrollers working together, that time transferring of those information is also important, right? So many protocols are there for transmitting of data from one particular embedded system to another particular embedded system, or you can say one particular MCU to another particular MCU, right? And even if it's not an MCU, sometimes we use those protocols to transfer data from one MCU to a PC also, right? So the common communication protocols that we use are UART, SPI, I2C, USB, Ethernet. Okay, so MCUs can talk to a sensor. Okay, there are many sensors which can read the analog data, okay, convert it into digital format and transmit it to your microcontroller by using either SPI or I2C. Okay, similarly, MCU can utilize UART to send a serial data to your PC, so that you can read it using any serial software like EPOT or a Teraterm or a real term. Okay, similarly in car example I gave, right, you have multiple MCUs. Okay, so multiple MCUs communicate with each other using a kind of protocol that's called as CAN, control area network. That's kind of broadcasting way of communication, right? So you have different kind of communication protocols which are used in MCUs, right? So, and these protocols make the systems connected and intelligent. Now, amplifier peripherals are also one integrated part of the MCU. They are used when the input signals are very weak. So one example I told, like LM35 temperature sensor. So what happens is there, the voltage change with respect to the temperature is very weak, is in some microvolt range. So what we need to do, we need to increase the signal strength so that it improves the accuracy of the measurement, right? So for that purpose, amplifier peripherals are used. Okay, so very common example is, as I told, sensor signal conditioning and also in the audio system. So basically sometimes what happens, we use the mics, right? So they increase the strength of the audio signals, right? So consider the amplifier peripherals serves like a mic to a soft voice. So let's wrap it up by understanding this summary. Okay, so an MCU is a compact computer on a chip that can sense, process, and control. It combines core, which is the brain, okay, memory, which is the storage, input and output port, which is used for interaction with the external world, peripherals, which enhances the capabilities of the microcontroller. And what to understand is the microcontroller is nothing but the brain behind the modern electronics. If you want to explore more on this field in depth with structured learning and hands-on exposure, you can check out the complete embedded systems program. The links are provided in the description below. If you have any questions or doubts, feel free to drop them in the comments. And if you found this useful, like the video and subscribe to the channel for more technical content. Thank you.